Our next section is going to relate some of the concepts we've studied so far to graphs and what those graphs would look like as we plot them versus time. So we are going to look at position versus time, velocity versus time, and acceleration versus time. Each of these three graphs are going to have the same type of motion described on them. So for this example, we are going to have an object that is accelerating uniformly. That would be an example like you're in a car and you steadily push on the gas to accelerate the vehicle. One important thing we will be discussing is the slope. So look at this position time graph. You'll notice that as time goes on, the position steadily increases more and more with each time interval. So you should be looking at a parabolic shape. Now, I don't know if you've done a tangent line before, but if you were, a tangent line is a straight line that touches our curve at just one point. So right there. If we were to look at a tangent line further up, and looked at a straight line that touched that curve just at that one point, notice that the steepness of it is changing. So we should look at the slope of these straight lines that we drew. So let's do that. You should know by now that the slope is equal to the rise over the run. Well, in this case, our rise is the change in position. So I'm going to do a change in d over the change in time. Now, some of you may recognize change in position over change in time. We've also called this a displacement as well instead of change in position, but I'm hoping that you recognize that this is the velocity. So whenever we look at the slope of a position time graph, that slope value is going to give us the velocity. And again, if we have an object that's accelerating, notice that the velocity is one value here, but that slope has changed. We would have a higher slope, which means we have a higher velocity. And remember we said that the object was accelerating, so it had no velocity, then it had a little bit of velocity, then it had even more velocity. And we can see that as we go through the curve that the slope of that line is changing. The next graph is a little bit easier. If we were to graph the velocity versus time of an object that's accelerating, you'll notice that the velocity increases as time goes on. So this time when we look at the rise over the run, our rise would be change in velocity and the run would be the time interval. Now hopefully you noticed from the last lecture that you watched that change in velocity over time is going to give us the acceleration. And it is going to be a steady acceleration because our velocity time graph is one straight diagonal line. Lastly, when we look at the slope of an acceleration time graph, you should see that there is no slope to that. It's actually going to be 0. This tells us that by taking the slope of an acceleration time graph, we are not gaining any new information. You should have a chart in your notes, and so we're going to summarize what we have found by taking the slope of each of these three types of graphs. First, we had a position time graph, and by taking the slope, we could get the knowledge of speed or velocity. Remember that speed will be the absolute value, while the velocity does include the plus or minus sign as part of that value for the slope. When we have a velocity time graph, taking the slope will give us the acceleration, and you will have a plus or minus sign as part of your answer for that. And then lastly, when we looked at the acceleration time graph, we gained no information by taking the slope of that graph, so you can just leave that portion blank. Next, we're going to revisit each of the three types of graphs and look and see what the area will give us for each of those. Now when we discuss area, we're actually going to work backwards, and we're going to start with that bottom graph of acceleration versus time. When you see a question that asks you, find the area underneath the curve of the graph, don't let the phrase curve throw you off. It just means look at whatever section of the graph you have and see what shape that makes. So what we're going to do, this particular line was horizontal. So now when we look at the area under the graph, we would drop a straight line down. And then you can see that this gives us a rectangular shape. So if I were to ask you to find the area of a rectangle, you should know that we're going to multiply the length and the width together. We could also call that the base times the height. But the important thing that I want you to get out of this is when we multiply the base and the height, or the length and the width together, that's going to be our acceleration and our time value. So we're reading those straight off whatever numbers would be given to us on the graph. Now if you look at the acceleration formula, just recall that acceleration was change in velocity over time. If I were to rearrange this and solve so that I multiply acceleration and time together, that's going to give me the velocity. So if you have an acceleration time graph and I ask you to find the area under the curve, you should be getting a value for the velocity. And one thing to note is there may be a time when you are asked to find the speed instead of the velocity. The area will give you the same value for each of those. By finding an area, you do not have to distinguish between the scalar or the vector portion. So more than likely, you'll actually be asked to find the scalar version of whatever quantity is being asked for. So in that case, it would be speed for this type of graph. For the next one, move up in your pictures and your notes and look at the velocity time graph and drop a line straight down. This, you should see, gives us a triangular shape. To find the area, you would do 1/2 the base times the height. In this case, we would be taking 1/2, the base is the time, and the height is our velocity or speed value. I'm going to go ahead and jump ahead a little bit and show you some substitutions to get an equation that we're going to see in our next lesson. So this part is a little bit of a preview. Remember that acceleration was change in velocity over time. So if I rearrange this and look at the change in velocity, it would be the same as multiplying acceleration and time together. We saw that on the previous slide. So what I'm going to do, because we're starting at 0, our change in velocity is actually whatever that final velocity ends up being. So I am going to substitute in for the v right here. And that's going to give us 1/2 times time, and then AT. When you multiply these together, that's going to give you 1/2 AT squared, and what we're going to see is that this is another way to find distance. So again, this is going to be looking ahead a little bit to one of the equations that we're going to see. I just want you to be able to relate it to the graph. But for right now, whenever you find the area of a velocity time graph, that value that you're going to get for the area will be the distance. This last graph with position versus time, if we dropped a line straight down, you're going to have quite an odd shape with that parabolic motion. So without doing some really complicated calculus, we're not actually going to have any quantity that's given whenever we calculate the area for a position time graph. So this one we're not going to see anything as well. So let's summarize. In your chart, we would take the area to find the following. If it's a position time graph, the area is not going to give us anything. If you have a velocity time graph, the area will give you distance or displacement. And then if you have an acceleration time graph, you would be finding the speed or the velocity if you took the area for that particular graph. Next, we have an example problem to do together. In your notes, you should see a velocity time graph. Notice that the velocity counts in intervals of 5 meters per second up the y-axis, and time is counting in intervals of 1 second across the x. I chose this type of graph because we can get information from it by taking the slope and the area. So we're going to do an example with each of those types of things. I trust that you can follow along by reading your questions, so I'm going to go ahead and skip to the graph and give you a couple of examples and then see if you can do the other two by yourself. So let's get started. The first question asks you to find the acceleration from 0 to 3 seconds. Because this is a velocity time graph and we're looking for the acceleration, we should be finding the slope. Since we are asked to find from 0 to 3 seconds, that means that we are going to be finding the slope of this line from 0 to 3 seconds. So what we would do is simply say the acceleration is, and we have a rise of 20 meters per second and a run of 3 seconds. So this is going to give us a value of positive 6.6 repeating meters per second squared. The next part in the example question asks you to find the acceleration from 3 to 6 seconds. So that means we're going to be looking for the slope of this section right here. Hopefully you can tell that it has a slope of 0. So for part B, you would say the acceleration is 0 meters per second squared. Next, we're going to look at part C, the acceleration from 6 to 9 seconds. From 6 to 9 seconds, that's this portion right here. So let's look at our rise over run for those 3 seconds. There was a rise from 20 to 5, so we have plus 5 meters per second, and then our run was from 6 to 9 seconds, that's 3 seconds. You're welcome to leave this as a fraction, or you can change it to positive 1.6 meters per second squared. The last section that you were asked to find would be from 11 seconds, which is right here on the graph, to 15 seconds. So let's look at the slope for that one. To get the acceleration, we would do rise over run again, but our rise is actually in the negative direction. So we would put negative 25 up on the top, and our run is from 11 to 15 seconds, so that's 1, 2, 3, 4 seconds. So we would have negative 25 meters per second divided by 4 seconds, which gives us an overall acceleration of negative 6.25 meters per second squared. Hopefully that makes sense to you. So if you're given a velocity time graph, whenever you need to find the acceleration, you simply take the slope for that particular section or time interval. Make sure you include the plus or minus sign as part of your answer because acceleration is a vector quantity. Next, let's do the second question on distance. For this particular question with the velocity time graph, you are asked to find the distance for various time intervals. I am only going to do a few of these with you, and then I would like for you to try and finish out the other ones on your own, and then in class you can ask me if you got them correct. We can go over them if you need to. Since we are looking for a distance, I'm going to do part A from 0 to 3 seconds, which would be right here. So what we need to do is drop a line straight down from wherever the graph ends at 3 seconds, and we're looking at this shape. This makes a triangle. So in order to find the distance, what we want to do is find the area of that triangle. So I'm just going to scroll a little bit and go ahead and write in my formula. So if you look, we've got 1/2, the base was 3 seconds, the height was 20 meters per second, and I went ahead and wrote in my units so that you could see that those cancel, and this gives us a distance of 30 meters traveled in the first 3 seconds. The next section is from 3 to 6 seconds. So what I want to do is look at my graph and the shape of it for that time interval and drop a line straight down, and you should see that we've got a rectangle. So all we'll be doing for this section is simply find the area of a rectangle to get the distance. Be sure you're counting carefully. So from 3 to 6 seconds, that's 1, 2, 3 for the base, and then the height again is 20, so you should have a distance of 60 meters. I'm going to do one more with you and then let you finish out the problem on your own. Part C of the example asks you to find the distance traveled from 6 to 9 seconds. So if we look at the shape of the graph right here, you'll notice that if we drop a line straight down, it kind of gives us a weird shape. But if you go by the guidelines that I put in here, you can see that we've got a rectangle and a triangle. So what we would do is find the area for each of those and then add them together. For the rectangle portion, which is right here, I have a base of 1, 2, 3 seconds, and then 20 meters per second was my height, reading off the velocity axis. And then I'm going to add the area of my triangle, which is the shaded in portion right here. So I would be adding 1/2. The base is still 3 seconds, but my height is only from 20 meters per second to 25 meters per second. So I only have a height of 5 meters per second. Once you add the area of the two shapes together, you should get a total distance of 67.5 meters. Now go ahead and try parts D, E, and F on your own, and if you have any questions, make sure you ask me about them in class and we can go over them together.